Okay, let's talk about plasma. So remember that blood is mainly made of plasma, which is the liquid matrix of this connective tissue that we're talking about, blood. So the plasma is going to be clear to straw colored. It is the liquid portion, and it's about 55% of the volume of blood. The other 45% was the formed elements, the white blood cells, the red blood cells, and the platelets. Now, the majority of this plasma is 92, with 92% being water, but it also has a bunch of other chemicals in it. And those chemicals can be both organic or inorganic, and it's going to be all kinds of things. For one, you already know hormones, both lipid hormones and non-lipid hormones. And the lipid hormones are being carried by protein, so you should expect some of those in the blood, right? And it helps regulate the fluid and electrolyte balance and maintain the pH of the body. Now, these plasma proteins are proteins in the plasma, and they are dissolved. They are not usually used for any energy source. So here are the plasma proteins. We have albumins, which help maintain colloid osmotic pressure. Hopefully, when you hear the word osmosis or osmotic, you think of water. And what albumin does is it attracts water to it. And so that's what they're talking about, the osmotic pressure. When you have a lot of solute, a hypertonic solution, it will attract water molecules to move towards that area where there's less water molecules. And so that's what albumins do. Now, globulins, there's a few different kinds, but mainly two major kinds. Ones that transport those lipids and fat-soluble vitamins, and also the ones that are going to be antibodies made by those white blood cells. But most of these plasma proteins are coming from the liver, and fibrinogen, the one we're going to talk the most about in this unit, is what plays a role in blood coagulation. So let's talk about what most people think of when they think of what is dissolved in the plasma. Well, it's going to be the blood gases, and the major ones are oxygen and CO2. Remember, we're taking in oxygen through the lung membrane, the respiratory membrane, putting oxygen into the blood, attached to hemoglobin, and then moving that oxygen to our body cells so that those cells can burn fat for energy or burn sugar for energy. CO2 is the waste product of burning that sugar or fat, and therefore we need to transport it from our body cells to the lungs to breathe out. The nutrients found in the plasma, they could be amino acids or simple sugars, nucleotides and lipids, all stuff from what we've eaten. Let's talk about the NPNs, the non-protein nitrogenous substances. Of course, there's proteins in the blood, and proteins do have a nitrogen component, but not everything that has nitrogen is a protein. So that's what they're talking about, is what are the stuff in the plasma that has nitrogen but really isn't a protein. So these could be urea and uric acid, these products of breaking down nucleic acids or breaking down proteins. Amino acids, which is the building block of proteins but not a complete protein. Creatine and creatinine. Creatine is found in body cells, and it's where you get your boost of ATP for the first 7 or 8 seconds of activity. It can regenerate ATP super fast, and so but you run out of it pretty quick. So and then blood, urea, nitrogen. And this is urea. Anytime you see that, you should think of the renal structure, the kidney. And so you will find this nitrogen in the blood normally at a certain amount. But if you have too much of that, it can show that there's some kidney function abnormalities. So they call it BUN, blood, urea, nitrogen, or BUN. Also dissolved in this liquid are electrolytes. Now, electrolytes are the fancy term for ions because they ionize in water and can conduct electricity. That's why people call them electrolytes, but they're just ions, okay? So We get these from the foods that we eat and that we've absorbed in our intestines, or byproducts of the chemical reactions that occur in our body. And so the common three, I mean, huge: sodium, potassium, calcium, all of those very important for muscle movement and brain function. I hope you learned about that in Anatomy 1. Magnesium and chloride, also important. Bicarbonate, we'll actually speak to those in a second. And then phosphates and sulfates. All of those are going to be ions in the blood. So let's talk about a process now that we know what's in blood and what's in specifically the plasma of the blood. Let's talk about how we stop bleeding, a process called hemostasis. And there's 3 ways that we're going to try to stop blood loss. And these aren't in any specific order. In fact, a lot of them happen at the same time. But you're going to spasm your blood vessel. And so that's going to kind of think about that small, smooth muscle contracting to squeeze the blood vessel. Now, this is usually for smaller blood vessels, right? So we're going to squeeze it so we're not bleeding out too much. Our platelets are going to form a plug and plug up the space. So again, to stop bleeding. And then your blood's going to coagulate or clump together. And this is how we protect ourselves from internal bleeding and external bleeding of small blood vessels. So we'll start with the first one, this vascular spasm. If you cut or break the small blood vessels, the smooth muscle is going to contract rapidly. And this slows that blood loss. Also, as it contracts, those ends where the blood vessel was cut could come together and close completely. And it usually only lasts a few minutes, but can, be a while. And this allows time for that platelet plug to form and the blood to coagulate. And so it can be a temporary fix or a permanent fix if the blood vessel closes completely. Serotonin is released from platelets, and that causes this vasoconstriction, which will help initiate this reduction of blood loss. Now, platelet plug formation is pretty easy. These platelets are going to be exposed to collagen fibers, and they start sticking to those collagen fibers and just kind of make, like, if you will, a scab or something. Trying to think about how to picture it, but I think there's a picture soon, so you can look at it. But let's focus more on blood coagulation. This is the most effective, and it occurs in 5 to 15 minutes. And this is what you would consider a blood clot. And it has a series of reactions. We call this in biology a trophic cascade. It's where, like, one domino falls that causes another domino falls it's this series of reactions. And there's 2 methods of doing this. Extrinsic, which means from the outside. So something happens on the outside of our body and causes us to clot. Or it could be an intrinsic clotting mechanism, something from the inside. And all these chemicals that are used to help blood make a clot are called clotting factors. And vitamin K is the vitamin that is necessary for some of these clotting factors to work. It does depend on the balance between these procoagulants, which encourage coagulation, and anticoagulants, chemicals that prevent clotting. And so you can think about somebody who is on a blood thinner, they are going to have anticoagulants in a higher amount than the procoagulants. And so that's why you would be less likely to clot. Major event in conversion of the soluble, this is key. So major event, star this. We want to convert the soluble fibrinogen. So remember, in the matrix of any connective tissue, in the matrix, there's going to be the background stuff. So in this case, plasma, but also fibers. And we can see fibers in reticular connective tissue. We can see fibers really well in tendon, but we don't see them very well in blood because the fibers have not solidified. They're little tiny pieces of protein that have become soluble, and it's called fibrinogen. And what's going to happen is fibrinogen, these little soluble fibers that you cannot see, are going to become insoluble and stick together to form threads called fibrin. And they act like big nets. And that traps the blood cells, and that's what's called a blood clot. So here is a platelet plug formation and a blood clot. Very different things. A blood clot is going to be a web that blocks, kind of captures the blood cells and stops everything. But platelet plug formation is actually the platelets forming this plug, this stoppage to keep you from continuing bleeding, whether it be outside of the body or inside, like a bruise. So don't mix these up. They're both doing the same thing, but it's different ways of doing it. So we said there's 3 ways to stop bleeding: vascular spasms, platelet plug formations, and blood coagulation. And just once again, a platelet plug formation is when the platelets adhere to the connective tissue, or the collagen fibers in the connective tissue, and get stuck, and they form a barrier, kind of like bricks being built. But blood coagulation is where fibrinogen gets turned to fibrin and makes this big net and kind of blocks everything and forms a wall that way. So we're going to talk a little bit about extrinsic versus intrinsic clotting mechanisms. So it is triggered by blood coming in contact with tissues outside of this blood vessel, or the damaged wall of the blood vessel. And so that's where they're getting the word outside. So this is coming from the outside factors, and outside of the blood vessel, I should say. And the damaged tissue is going to release thromboplastin, sometimes called factor number 3. Remember, these are all called clotting factors. So this is not normally found in the blood. It's found where? Outside the blood vessels, in these tissues. So when tissue gets damaged, it releases that. And then that starts this cascade, this domino effect of several clotting factors being active. Thrombin, that underline, star, highlight this bullet. Thrombin is what converts fibrinogen into those fibrin threads. So you've got to have thrombin come into play. Those fibrin threads are going to keep the blood from moving and eventually trap all those cells and platelets and make that blood clot. This is an example of positive feedback. We don't see positive feedback a lot. Remember, we saw all those negative feedbacks in our endocrine system? Well, this is an example of positive feedback. Once clotting begins, it actually promotes more clotting. So once you form that net, it's going to stop blood, which stops more blood, which stops platelets, which stops more blood. Intrinsic clotting mechanism starts within the blood vessel. So intrinsic, inside of you, inside of the blood vessel. And so we're not having any tissue damage. If we had tissue damage, then factor 3 would be released and cause the cascade. So what activates intrinsic clotting mechanisms? Well, it's activated when blood comes in contact with some surface, like collagen in your connective tissue, instead of the blood vessel wall. And this is triggered by factor number 7, which is found inside blood, and they call it Hageman factor 7. As in that other clotting mechanism we talked about, this starts the sequence of several clotting factors being released. And once you get to factor X, this cascade proceeds the same way, and you end up making that fibrin mesh and a blood clot. So blood coagulation is making a blood clot. And it can be extrinsic, outside of our blood vessel, or intrinsic, within the blood vessel. And what starts it? Thromboplastin and Hageman factor 7. And then you have these series of chemical reactions that occur. Prothrombin turns to thrombin, and then thrombin, remember what we said thrombin does? It causes fibrinogen to become insoluble and form fibrin, and then those are going to be your webbed pieces that hold it together. Now, this is what the domino if you set up all the dominoes, this is kind of what it would look like if you looked from above. And so right here is extrinsic, and then here's intrinsic. So let's look. If the tissue is damaged outside of a blood vessel, those tissues release that factor 3. And when factor 3 comes into contact with another factor in the blood, it activates calcium 2 ions. Remember, we have ions in the blood? Those ions activate factor X. We said that was important. Once you get to factor X, you're going to make prothrombin become thrombin. Now, here's all these other things coming into play, but the big picture is once you get to factor X, think about X marks the spot, you're going to eventually have prothrombin turn into thrombin. And once you have thrombin, it converts fibrinogen into fibrin. And once you have fibrin, we're going to make that fibrin clot. If it's intrinsic, blood somehow come in contact with some foreign substance like collagen inside the blood, and that activated Hageman factor 7 to be released, which activates another factor, eventually getting us to that X marks the spot, that factor X, where prothrombin turns to thrombin and activates fibrinogen into fibrin to form our clot. So here are all the names of the clotting factors. If you care to know, do not memorize this for anatomy. This would be in med school somewhere, I'm guessing. I've never had to memorize these, but yeah, just FYI, fun to know. So what happens to these blood clots? We know how blood clots made. Well, after the blood clots form, it starts retracting. It's almost like drying up, and it pulls the edges of that broken blood vessel where it's attached, and it's squeezing those two sides together. Now, serum is the plasma of the blood, but it doesn't have fibrinogen and all of those clotting factors. So we're squeezing out the serum. And then there's a platelet-derived growth factor that stimulates your smooth muscle cells to start repairing the damaged blood vessel walls. Plasmin is something that digests those fibrin threads, and that's what dissolves the clot, plasmin. There are some abnormal blood clot formations, and you do want to know these, especially if you're heading to nursing, right? So what is a thrombus? It's just an abnormal blood clot that forms in a blood vessel. An embolus is a blood clot moving through the blood vessel. I wish I had ways for you to remember all this, but I really don't. Thrombosis is blood clot in a vessel supplying a vital organ. So it's blocking oxygen carrying blood cells to an organ. So remember, osis is a condition. Infarction is death of the tissues which have been blocked, you've had thrombosis, which causes an infarction. Okay, so tissue starts to die. Now, embolism is a blood clot that travels and then blocks a blood vessel in an organ. And atherosclerosis is where you accumulate fat inside your arterial lining. It reduces the diameter, and this can cause the intrinsic mechanism of clotting because of the fat around the arterial lining. And so that would cause an abnormal clot formation, which is how we get a thrombus or thrombosis. So what's also real important for you to know is that what atherosclerosis is. And so atherosclerosis is this buildup of a plaque due to high cholesterol, usually in the diet that eventually goes into the blood. So this is what a normal artery looks like. Here's the artery wall, and here is the lumen, the space in which blood can flow. Notice when you start building up this plaque due to atherosclerosis, the wall is pushed against, but what changes the most? The space that the blood can flow through. And so if you can't put a lot of blood through here, you're already starving those tissues of oxygen. And then think about this: if Hageman factor 7 touches this edge, or some collagen gets stuck there, then you can start clotting this artery, which could be really bad. You've probably heard of deep vein thrombosis, or DVT, and this is something I really pay attention to when I take people out of the country. This is when you form a clot because of pooling of stagnant blood. It's going to usually be in a deep vein, like the femoral or popliteal veins, deep veins of your pelvis. And a real serious one is the pulmonary embolism, in which the blood clot can travel through the circulatory system and it will lodge in your pulmonary blood vessel, so your lungs. And so now you're not going to be able to use lung function correctly. And how does somebody have a lot of blood pool? Well, oftentimes we see this on airplane flights. Now, our longest flights this summer are going to only be 9 hours. I've been on a 14-hour flight, and I've heard of flights longer. And I always encourage my travelers to not sit in their seat the whole time. True story, I did that. It was my first time going to Paris. I was by myself. I didn't really know any better, honestly. Biology really is hard to apply in real life when you're in a situation, kind of like when your baby has fever, and a little fever is okay, but you want to get it down, but you don't because you're a mom. Anyway, so you don't think about biology is my point. Sorry, squirrel. But so I have my people who travel to get up often, go to the bathroom, even if you don't really have to. If the person next to you get up too, and make a lap around the plane so that you can move your blood. Blood is only moved, as you learned in Anatomy 1, in veins. There's no pressure, so you've got to use your muscles squeezing the blood and milking it back up, or it's going to pull in your feet. So what are some symptoms of this? Deep muscle pain and cramping, swelling, phlebitis. A clot could break off hours or even days after it's formed, after your long flight. And so you should, if you're prone to clotting, take some anticoagulants. Wear compression stockings to help push even small movements of your muscles, like in your seat, can help push blood back up from your feet towards your vena cava. And then, of course, exercise while you travel. I actually do yoga at the drink station. People always laugh at me, but I haven't had a clot, knock on wood. So how do we prevent coagulation? The smooth lining of normal blood vessels discourages accumulation of platelets and those clotting factors. And that's why a healthy arterial is important and not an atherosclerotic one. So it says healthy endothelial cells produce PGI2, and that is a prostaglandin that prevents platelets from sticking to the walls of a blood vessel. As a blood clot forms, fibrin absorbs the thrombin and prevents the clotting reaction from spreading. Antithrombin inactivates the additional thrombin, so it kind of stops this fibrinogen getting turned into fibrin. Some cells, like basophils, remember those? And you might have heard of mast cells from Anatomy 1. They secrete heparin, which is an anticoagulant. So there's chemicals and processes that are at place to stop you from getting a clot from sitting there too long. Of course, if you don't have healthy blood vessels, they don't work as well. So here are factors that inhibit a blood clot and how they work in a nice table. And here are some disorders of the blood. So like sickle cell disease, you've heard me, I'm very interested in that. We've talked about what causes that. Hemophilia is where you lack specific clotting factors, and so you never get to factor X, and you have internal bleeding. There are several types of this. They're often in males because it is hemophilia is a gene found on the X chromosome. And females, we have two X chromosomes. So we're more than likely to have one of those X's normal, where males only get one X chromosome. And so if they get an abnormal hemophilia, gene on an X, they don't have another X to cover that up or to use. Erythrocytosis is where your reticulites have extra EPO receptors, and so that enhances your stamina. Fun to know, don't need to know all of these. So our last little bit is talking about these blood groups and transfusion. Back a long time ago, 1910, they identified the ABO blood antigen gene. And there are other types of blood groups, but ABO is the one that we most common talk about. When you're talking about blood types, you're talking about the ABO. So they are distinguished because you have these little proteins called antigens. Antigens can cause a immune response. That's anything that can cause an immune response. And for blood, it's these proteins on the outside of the red blood cells. And these proteins are inherited. They're in your genes. And so a safe transfusion is important, that the donor's blood does not cause a reaction and is cross-matched. And so if it is, the recipient's serum will start clumping those red blood cells through a process called agglutination, using those gamma globulins in the plasma. So some vocab word to get down, we'll see these come back up when we talk about immunity. Antigen, like I mentioned, is any molecule that causes an immune response. In this case with blood, it's the proteins on the outside of the blood cells, the red blood cells. If the immune system finds this foreign antigen in the body, it will produce antibodies and start fighting whatever that is. So you can imagine if you receive blood that has these little proteins that your body doesn't know about, it's foreign, and you will fight those blood cells. And I'm going to guess if you're getting blood donated to you, there is a problem. You need blood, and fighting and coagulating that blood probably wouldn't be a good idea. What are antibodies? Well, antibodies are these proteins in the blood plasma made by B lymphocytes, one of our white blood cells. An incompatible blood transfusion is when donor red blood cells cause an immune response in the recipient. Agglutination is what will happen. I said coagulation. I should have said agglutination. And this is just how we clump red blood cells together with an antibody. And so only a small number of antigens on red blood cells will evoke a series transfusion reactions, and those are the RH antigens and the ABO antigens. That's why I talked to you about there's other blood types based on other things, but they're not as important to us because they aren't potentially deadly. So a transfusion reaction will cause anxiety and breathing problems, facial flushing, headache, severe pain, and could be jaundice. Okay, so let's talk about this ABO blood group. It's all about this protein on the red blood cell called antigen A or antigen B. For example, my blood type is AB. So my blood cells, all of my red blood cells, have some A's and B's on the outside of the membrane. Okay. Let's just go to this. I don't ever want you to memorize a table per se like this when you can understand it. Let's go here. So where am I? I'm AB. So I have both A and B little proteins that poke off. Okay. So I don't make any antibodies to fight A because I am A. I also don't make any antibodies to fight B because I am B. So that's why I can receive A blood, B blood, AB blood, O blood. I'm called the universal recipient. Let's go to O blood. O blood, I think they wrote a 0 and somebody read it O because A, B, and 0 don't make sense. But think about type O blood has 0 proteins on the blood. It's a smooth membrane. So, antibodies fight anything that's not you. So, because they don't have any A's, they're going to fight A's. And because this red blood cell doesn't have any B proteins, it's going to fight B proteins. And so, if I donated blood to you and your O blood, your antibodies would quickly fight my blood cells. Your A antibodies and your B antibodies would fight my red blood cell because my blood cells have both. So you cannot, as an O blood person, you cannot receive AB. You can't receive A because look, if this blood gets into your body, you're going to fight it with your A antibodies. And same thing. So O blood can only get blood from who? O, because it's fighting all the antigens, so you can only have blood with no antigens on there. However, because there's no antigens on here and there's nobody to elicit an immune response, this blood can be donated to all the other blood types, and that's why it's called the universal donor. If you're type B blood, it just means you have these B antigens, so you fight A. And if you're A blood, it means you have the A antigen, so you fight B. And that means A can receive blood from O because it doesn't fight O. How do you fight nothing? It can receive blood from A, but it cannot receive blood from B because it has the anti-B antibody. And it can't receive blood from AB because it has the B antibody. So let's go through this. Looking at this picture, if you're blood type A, you have A, so you're anti-B. So you can have any blood as long as it doesn't have B on it. If you're blood type B, you have the antigen B, so you are going to be anti-A. And so you can get any blood as long as that blood does not have the A protein on it. Me, if I'm AB, I have both antigens, so I don't fight anything. So I can get any kind of blood there is. O blood has neither antigen, so who they fight? Everybody. So they can't get any other blood that has any A's or B's on it. They can only receive O. And then this is just kind of interesting, the frequencies. I'm kind of a weirdo. Only 4% of Caucasians are AB. If you'll look, the most common blood type in all the groups is O. And so if you're O blood, while, people go, oh, which one's better? Well, O's pretty good because there's a lot of you and you can donate blood and help, because who can get O blood? Everybody. So please, I encourage you to donate blood if you can, and especially if you're type O. Well, people worry, oh gosh, I'm type O, I can only receive O blood. Well, that's who most people are. So most people are donating O, they're good. Who wants me to donate AB? Not many people, honestly, because who can get AB blood? Only AB folks. And there just isn't a whole lot of us. Did I mention I'm a weirdo? So what is agglutination? It's when these antibodies come in contact with the antigen. And so, for example, you have a person that's type A. How do I know they're type A? Because they have an antigen A on the red blood cell. So what are they? They're against B, right? So you give somebody the blood, and look, if this blood is donated to someone else who is anti-A, it will start clumping the blood up. Look at this one antibody is capturing multiple cells. And so you start to have clumping. This is a normal blood transfusion. Ooh, look at these white blood cells. Hope you recognize some of them. Look at those granules. So you could say it must be a feel, right? Here's where the cells have gone through agglutination because of a mixture of the wrong blood. So again, the universal donor is type O and the universal recipient is type AB. And if you still don't understand why, you can pause the video and read that. And this is all the permissible blood types. So if I'm AB positive, so I can literally get anything. Now, how does RH happen? Because that's what this negative and positive mean. RH is just another shape protein. So if you're RH positive, it means you have that shape, and so you don't fight RH. But if you're RH negative, you do fight RH. And so RH positive is the presence of this antigen D or RH antigens on your red blood cell sticking out. Now, real important is erythroblastosis fetalis. This is hemolytic disease of the newborn. And this is a serious condition where an RH positive fetus was carried by a RH negative mother. Why is that so bad? Well, the RH negative mother is negative for RH. So who does she fight? She fights RH positive. And those antibodies actually can cross the placenta. And so what will they do? They will wage an attack on the fetus. And the first pregnancy, it's not as big of a deal because the baby grows faster than the mom can fight it. But in the next pregnancy, the mother has all these memory cells and can actually attack the fetus much quicker. And so this is a rare condition, and because we know how to stop it. The very first thing that happens when you get pregnant, guys, I'm talking to you, and ladies, I'm talking to you if you've not had children. One of the first things that happens when you're pregnant is they blood type you. They don't really care about the ABO stuff because those antigens don't cross the placenta. But they are checking to see, are you RH negative? If you're RH negative, you could build antibodies to fight your child if the baby's positive. Now, if the baby's negative, you won't. But are they going to check the blood type of the baby? No. So if you're RH negative, you get RhoGAM, RHOGAM. RhoGAM, name that after RH. Now, if you're RH positive, you're not going to fight RH. You're not going to make antibodies against RH. They're not going to pass through the placenta. So your baby's good. I am RH positive, so I didn't get that extra couple of shots. So this is showing an RH negative female and an RH positive baby. And so she is going to build immunity to attack the child. Maybe not the first time, but the next time. It says the female becomes sensitized. Really, she has what's called memory cells in there, and she can react much faster. So she will abort this baby spontaneously. And that is the end of this chapter. So you have some labs to do, you have a practice to do, and your first unit test is over hormones and the blood that carries them. If you have any questions, I really do invite you to ask those and send me an email, and I will help you the best I can. Good luck.